slowly getting caught up on grading, but maybe we have so many assignments coming in that it's hopeless. But I am trying to get some feedback back to you. So anyone that is either turned in a written project status report or a met with me during office hours should have gotten some feedback. If you just turned one in, I haven't gone back and downloaded them again. But and I have been through the first two research reviews plus the graduate students have their additional ones, right? So they have graduate students are doing 10, the undergrads are doing 5. So I've done 3 sets, and we'll try to keep up with that. So I also graded the FMCW radar one. We didn't do too well on that one. I didn't do too great a job teaching it, I guess. And all, there were a couple of people that got almost everything right, and that was great. But a couple of notes on this. I know we've already kind of beaten this one to death, but it's still useful to remind you to show your work on any type of assignment like this, right? So whether it's my class or anyone else's class, you want to show the formula, right, in basic form and variable form. Then you want to show the values subbed into that, and then show the answer, right? If you have some intermediate steps, show those too. That's great. But the keys are, any instructor or whatever is going to want to make sure that you're understanding which formula to apply in which case, and then how to apply it, right? Interpreting the variables and picking out the data and that's given in the problem and properly getting those substituted in. All right, so that's just procedural. The one thing I do want to note is that a lot of you, when you looked at the sample rate, looked at the RF bandwidth, right? And maybe you got that calculated right at 750 megahertz. Maybe you did something else and came up with a different number, but you would look at that and say, oh, my sampling rate needs to be twice that. That's fine if you're using real sampling. But the point is that we're not, in the radar application, we're not sampling the RF signal. We're sampling the IF signal. So you really need to be looking at the IF bandwidth. And I don't always ask the questions in the same order, right? That's up to you to figure out the right order to solve the problem in, right? So you're going to figure out the IF bandwidth, and then that gives you your answer to the sampling frequency, the sample rate that you need for that. Also note that some of y'all came up with some different equations. Maybe you have a background in radar, maybe you looked up some radar equations. Understand that chirp radars, FMCW radars, don't necessarily have the same type of relationships between pulse width, pulse repetition frequencies, these type of things that maybe we're used to dealing with in radar. And FMCW radars just work a little bit differently. And for example, your pulse length, the chirp length and time, T sub C, is really driven by your velocity resolution that you want to be able to get out of the system. So, all right. But that's all water under the bridge. It's kind of hard in a remote synchronous type learning here to drive that home, but I'll take ownership of maybe not explaining that problem well. I have a 6th homework assignment in mind, and basically it would be you could choose to either do a reinforcement learning run through or an object detection or something like that, and just run through the software, or you could do like some ROS exercises that we're going to talk about today and let you choose one of those. It'd be more like a lab than a homework assignment. I don't, so I could do that, but I feel like we really need to work on the research reviews in a project. So I will, I'm going to put up a poll and I'll leave it up here. I haven't done this on Google Meet in a long time. Should we do another homework assignment? All right. And we'll say yes or no. All right. So, and yeah, response appears without names. I don't care who says what, but yeah, do that poll. I think we can do that while I continue to lecture. So, talked about the homework assignments and I talked about the grading. So, let's talk about the research reviews. So, we're getting better at them, and that's the point. This is a learning exercise, right? So, if yours, the first one came back all marked up and low grade, whatever, it's you hopefully you are learning as you go through. Actually, I think I was super forgiving on the first assignment in terms of assigning grades, but now I'm a little bit more particular. So make sure that you, on any assignment you turn in, you put your name up there, and maybe the course name and the or number and the assignment title and the date. Right? These are basics. Just get in the habit of doing that. It's just good practice. First of all, it's good discipline, and second of all, it's kind of a pain when I've got a whole bunch of things up there, everyone's assignments, and I'm trying to grade them, and I'm trying to keep a rhythm going so I can grade everyone's fairly and not get biased, whatever, right? So, and then I don't know whose is whose because there's no name on it, and I've got to go and do some detective work on that. So but that's again procedural. So let's talk about the research reviews. Right? Again, you're not writing a research report, you're writing a review of other people's research publications. And I think we're generally getting that at this point. So part of it is a learning to just by reading lots of different research reports on the same topic, you're going to learn about that topic. Right? That's one goal. The other goal is to teach you how to critically review other people's research, right? And because not all research out there is created equal, right? There's good research, there's good papers, bad papers, everything in between. So when you're writing this review, you want to, well, first of all, get the citation up there, right? And we're pretty good at that now. Everyone's got a citation. Sometimes they haven't been great citations, and also I've tweaked those a little bit, but we're doing pretty good on that. But generally towards the end of someone's introduction, also in the abstract, they're going to talk about what the main contribution of this research paper is, right? It's rare that you're going to get a research paper accepted for publication either in a journal or a conference or whatever, unless you're presenting something new. Now, it might be a new analysis of someone else's work. It could be a new survey where you're surveying other people's work, but you're doing it in a new way, something. But generally, it's new research, right? what problem are they trying to solve, and how are they solving it? And when you're looking at how they're solving it, it's like, what is the main contribution of that paper? In a lot of cases, they will enumerate it, right? Because when they're submitting their paper, they're submitting it, and some reviewers are going to read that, and they're going to try to decide, hey, is this paper worth accepting for publication or presentation? So when you write a paper, you want to make it easy for those reviewers to say, yes, hey, this is new, right? So most of us will, towards the end of the introduction, we will kind of highlight what the main contributions we think are of our work that we're writing up. And then you might, for a longer paper, you might have kind of an outline of the paper to come. So, you can copy and paste that in, format it, put it into your own words or something, but that's one of the things you really want to latch onto. I know that some of the reviews kind of ramble and try to hit, some points and not. And okay, I get it. Maybe you're pressed for time and you're trying to skim over these things as quickly as possible and you're trying to pull this out, right? So do yourself a favor, focus on the end of, typically this is where people put it, near the end of the introduction. They probably also put it in the abstract. Look at that, pull that out, put that in your review. Then everything else is going to kind of follow on that, right? So they're going to have a related work section. That's important if you're really going to dive into like implementing their research on your own. Then you're probably going to want to go and make sure you've got great context and understand, okay, what was done before, what are these guys doing new, what's that kind of foundation that they're building upon, that type of thing, right? But really what you're looking for is a description of their real contribution, right? So we pulled out the kind of bullet points of it. It might be 1, 2, 3 type of things. Now you look at what is that they're really doing. And what I want to see in these reviews, particularly for the graduate students, right? I'm required to set a higher bar for the grad students. And part of that is just because they're cross-listed courses, and we've got to make sure that the grad students are doing, grad student level work, and the undergrads are being held accountable for undergraduate level work, right? So, but part of that is doing 10 versus 5, but also just make sure that you are describing the research. Now, I don't need every single formula, every single nuance of it, but I want you to put into your own words what their method is, or their technique, or their process, whatever it is that they're bragging about in writing this paper, right? So make sure you write that up. And these are the important things. And then after that, it's kind of context dependent. I've given you some ideas in the assignment. Don't feel like you've got to match each of those things up. Some of you are doing that. It's okay, but those are kind of suggestions, right? And it may not always apply in every single paper. So when you look at a paper, typically they're going to have some new theory, new process, new method. Then, so you're going to describe that. Then they are, especially for the longer papers, a journal paper in particular, they're going to go into showing you or proving that it's better, right? So mathematic papers actually literally do proofs, right? But typically in engineering papers, you might see a few proofs, but you're going to see a simulation or an experiment, or maybe just kind of like a proof, but an analytical derivation, and they're gonna derive some formulas and say that's it. Okay, trust me. So, but I want you to look at the papers and understand. All right, they did a simulation. Right now, when you do a simulation, you're not simulating the real world. You're making all sorts of assumptions and simplifications and that type of thing, right? So maybe they've done that in their theory also, right? And of course, we've talked about this before, but the classic thing is that, you know, when you're a sophomore and junior, you talked about linear time invariant systems. Well, guess what? In the real world, they're not linear. Things are nonlinear. Things vary with time. They're I don't know if you guys have studied stationarity yet. Things aren't always stationary. Hopefully, they're wide sense stationary, but not even then, right? So, but you want to see what kind of simplifications did they make in developing their theory, and then what kind of simplifications did they make when they actually ran the experiments, and try to, this is where you're going to sharpen your critical eye. Did they, you know, you can kind of write a simulation that's going to give you the results you want, right? So, or are they really honestly giving a true simulation that's really testing it out well? And what kind of conclusions are they making? And then, you know, or, you know, what's the kind of end result of all of this? Right? And then there's that chance for you to add in your own kind of thoughts, like, and I know it's hard unless you've actually been looking at this stuff for a while, but as you get towards that 5th or 10th paper, that's where, you know, hopefully you've seen kind of a body of work in a particular area, and you're starting to see, okay, how is the progression of research going, and what is maybe that next step, right? Loosening up one of those simplifications that maybe they made, and or accounting for nonlinearity where before they just did linearity or something like that, right? Or scaling it out, expanding it. So okay, but by and large, people are getting the hang of it. This is great. On the projects, I want to just mention a few things there. The project's yours, right? So you create the project the way you want it. What I'm going to be assessing is maybe not that you spent 3 weeks optimizing something and you got 0.999% accuracy on some machine learning metric. That'd be great if you did, right? But what I want you to do is I want you to explore, right? So as you hopefully at this point, you've got some significant part of your project running, okay? And now what you're going to be doing is you could continue to optimize it, but consider like toying with it, playing with it, and exploring with it. You know, for example, in a machine learning application, instead of maybe training to 1,000 epochs instead of 500 epochs to try to squeeze out a little bit more accuracy, maybe play with some of your hyperparameters, your learning rate, you know, change that around a little bit, or some dropout rate or something, right? So everyone's project's a little bit different, so I'm just giving you an example, but I want, in the end, I want to see that you've done some body of work and you've got something working. But you're going to be writing this up and turning in a report. And I want kind of a like a lab report in a sense. You know, think of it in terms of that way, but a project summary report, where I want to understand your experience and what you did and what you looked at, not just the end result, but did you have to try 5 different learning rates before you got it to converge, or that type of thing, right? So, and I want your source code, and I want some sort of, maybe you take a little video of it, or a picture of something working, or some output charts that show accuracy over time or epochs, or something like that, right? Figure out what is a measure of your work. I also want your source code and a link to your training set of some some way or some other. Probably by now you've got GitHub accounts somewhere, so you can just put it up there and send me a link to GitHub. But if not, whatever works, send me your code. And since we don't have a final, I feel like I can take you right to the limit of the semester, and so if you're done earlier, turn it in. But yeah, by the end of the semester, it needs to be in, and then I can spend a few days grading these things. So I think my grades will need to be in on Thursday night of finals week, technically. So, yeah. So the other thing I'm going to look at, I think I've danced around this, is that how much did you really explore here, right? So, or did you just grab some code off the internet, got it working, said, that's good enough, I'm going to go work on some other class, right? I want to see that maybe you took code off the internet, that's fine, but what did you do with it? How much did you explore it? Did you change things? Did you try different things and that type of thing? Right. So first get things working, then explore a little bit, right? So, all right. Hopefully that helps. So let's move along here. Last week, we had just gotten to the point of looking at some deep learning, and in particular actor critic, and making sure that so you're seeing the right thing. So I talked about so there's lots of different ways of taking kind of the basic reinforcement learning techniques that have been around for a couple of 3 decades and adapting deep learning techniques to them, right? And deep Q learning is a big one, where instead of having a table of Q values that are state and action pairs, then you, instead of having a table, which kind of forces you into these discrete type states and action pairs, then, and the real world, until you get down to the quantum level, really isn't discrete, right? It's continuous. So we use neural networks, deep neural networks, to do this function approximation, to basically do that lookup table, but do it as a neural net, right? And now we can scale into much finer states and actions and that type of thing. Then we have, by using that neural net as a function approximator, then we have dueling Q, deep nets, and a bunch of others that I grabbed an example of this actor critic network, and it's just a sample here. And because I had to restart my computer, I kind of lost it, lost the training on it that I'd run, but I've done that now so we can see it. But it's got a couple of dense connected networks, and then we've got the value and the policy outputs, right? For this is kind of implementing that actor critic, the actor that figures out what the, let's see, it's basically implementing this type of thing, right? So the actor is figuring out the right action, the critics assessing the value of things and then feeding that into the actor, right? Using this type of, right? So that's what this is doing, and we're using a Keras kind of helper system in TensorFlow, and this uses some tricks with this gradient tape, which, if you're into doing TensorFlow, then you might find there's an eager mode and a non-eager mode, and this gradient tape has to do with that. So just only worry about that if you're really working with TensorFlow. So then we go and train it, right? So we have a main program, and it goes through and trains this. And so that just takes a long time. So, well, it wouldn't have to. It's an 1800 episode epochs of this thing, right? So we see here about halfway through, we start really getting there. There's still some variation and all, but then we get, and I just wanted to be able to show playing the game. So now I'm going to, when we finish training, we close the environment. Now I'm going to open the environment, but have the render mode as human, so we can actually see it happening. If you had render mode human while you were training, it would take forever, because that's really slow to render that, right? But I create things again, create an agent, and I load the checkpoint, right? So that's where as we were training, every time we got a better result, then we would save that as a checkpoint. And so when it finishes, hopefully it has the best model to use, right? So that's what we're doing here. This is very similar type code as the training loop. I just copy and pasted, but I set load checkpoint true, and I just comment out some stuff. But now we can actually see it run. So hopefully. Well, where did it go? There it is. Okay, so you see this, I don't even know if I had time to really explain what was going on, but the idea is that there's a pole, like a telephone pole, pivoted on top of this cart that's got to go left and right, and it's got to balance that. So it's got to move one way or another to try to keep that telephone pole upright. So as soon as you get too far over, it's gonna fall over. And you don't quite see it fall over because the game ends so fast, right? But all right, so I just ran 10 times, I think. Yeah, 10 times. So just wanted to finish up with that. And then we can, I hate that it doesn't go away, but we'll kill that. So let's now, so we're kind of now ready to talk about edge computing, right? So let's dive in here, and we lecture 11. I think that should be at lecture 12, actually, because we're about a week behind. So actually, I'm not going to talk a whole lot about information flow other than in the context of a CAN bus, computing hardware a little bit. We'll look at NVIDIA and just maybe touch on Tesla's, and then mostly look at the robot operating system ROS, but also I'll talk a little bit about Moose IVP. So the CAN bus stands for Controller Area Network, and it goes back to 1983, but I think it was originally developed by Bosch, and then they kind of opened it up and turned it over to a standard organization. Originally, it was on big, huge equipment like big construction equipment or very sophisticated vehicles, that type of thing. But now it's on lots and lots of different vehicles. So it's very super common. It's used to efficiently and reliably move information around the vehicle. Okay, and so it's standardized by ISO, International Standards Organization 11898, and hopefully you've been talking about standards in your capstone class, so you understand a little bit about that. Defines some aspects of the physical layer, the PHY layer, but there is some flexibility there. And but so mostly focuses on the data link layer, protocols, and messages. Okay, where are we at here? So it's a serial interface, serial bus with carrier sense multiple access with collision detection and arbitration on message priority. Okay, that's a mouthful. CSMA, it's even a mouthful in acronyms, right? So, but we can kind of walk through this a little bit. Has non-deterministic latency in its basic form, meaning that um, since there's possibly many different sensors on a car, and they're all publishing data and onto this CAN bus, and there's different actuators that might be pulling stuff off the CAN bus, then uh, you might have some situations where, because you're having to contest to arbitrate who gets control of the bus at any given time. So you might have non-deterministic latency. So in other words, that it's a little bit random on what the delay is between when you send a message and when it's received. So there are some enhancements for real-time control. For example, time trigger CAN, TT-CAN, and this is addressing this non-deterministic latency. And basically what it does is it has some exclusive time windows for specific periodic messages. So you don't make everything time triggered or time sensitive. You figure out which ones are important for me to really have some deterministic, consistent latency, and they allocate those to these handful of windows, right? So then everything else is going to be the conventional arbitrating time windows, right? So if you're using a time trigger CAN, not everything is going to be time triggered, just your important stuff, right? So the physical layer can take multiple forms, but very typically it's shielded twisted pair using a modified form of differential signaling for noise immunity. Noise is a big deal in vehicles. You even in gasoline or diesel engines, you're going to have an alternator running. That generates lots of electrical noise that's going to get into your wires, and electric cars potentially even worse, right? So your wiring needs to be shielded, and if maybe you studied this and applied electromagnetics, but if you twist two pairs, then you send a differential signal on there, they can kind of mutually shield each other. So so that's typically used there for noise immunity. And then if you remember back to your digital logic course, what was that, first semester sophomore year, then you probably studied tri-state logic, right? So you'd have a logic that might be low or a logic that would be high, and you could also have logic that maybe is passively sitting on a line because it's not active right now, and it goes into a high impedance state. We call the tri-state, or the implements a tri-state type thing. Different but similar here. In this case, we have a recessive state where the signal lines remain in the high impedance state, and then we have the dominant state, and the signal lines move to a low impedance state and when they're signaling. Okay, not going to go into a ton of detail on this. I don't think anyone's project is really involving CAN, but it is ubiquitous out there, used for a lot of different things, so you should know about it. You can, the speeds are going to depend upon which form of the phi layer you're doing and stuff, but you can get up to like 1 megabits per second over 40 meters with a maximum of 30 nodes. And so just like any standardized thing, you want to have, you want to adhere to the standard in a certain way so that you can be compatible, right? And you can build a CAN-based sensor, a CAN-based actuator, and You can sell that to a car manufacturer. They can include it in the vehicle, and it'll work with all the other sensors and actuators and controllers and that type of thing from other vendors, right? But there's still going to be some proprietary type of thing of some of the CAN vendors that are selling chips or ecosystems around CAN and that type of thing. So, all right. So here's from TI a description of this kind of inverted logic. So in this recessive state, we're not hanging on, we're not holding the bus at any particular point, but then in the dominant, so you note that it's active low type of signaling here. So we're going to pull that low. So there's some pull-ups in here, but we're the other thing to note here is that we transmit onto the bus and we simultaneously listen. Right? So this guy is going to be listening to the bus while we're transmitting, and that's important to help us do the arbitration, and actually the collision detection part of the arbitration. So we're listening, we can hear if someone else is talking also. So, all right, performance is important in CAN applications. So we want to do this bus arbitration right. We don't want the system thrashing because everyone's kind of fighting to talk, right? You ever been in a group of people and you got that one person that's always talking and never shutting up, and it's hard to get a word in edgewise, right? So we want to avoid that to a degree, but we also want to avoid the problem of having a centralized scheduler. In a system like 5G cell phones, we have a centralized scheduler that operates in most aspects of that communication. And it tells the handsets when they get to talk and how they get to talk and stuff. So, but that requires a lot of infrastructure, and we don't want that in CAN. We want a much lighter weight type thing. And so it's more like Wi-Fi, where they're going to, you're going to try to talk whenever you need to. On an event basis, when you need to talk, you're going to try to talk, but you're going to monitor whether someone else is trying to talk at the same time. So what we need to do is we need to wait and monitor that bus for inactivity for a certain period of time before attempting transmission. Then we're going to start trying to talk, but we're going to go through this arbitration process, which is non-destructive and bitwise. I'll show that in a minute here. And the node with a higher priority message wins and keeps transmitting the message. Okay, so this is new, this higher priority. So we can assign different priorities for different different messages or different sensors or that type of thing, right? So here's the example of two different nodes trying to talk at the same time. And so node C is starting to transmit, node B is starting to transmit, and this is the arbitration bits that we're sending, and the nodes with the higher priorities have more actives in their arbitration sequence, right? It's part of their ID, their identification. And so they both start talking, but they're both still listening while they're doing that. And B stops, right? They've sent their little ID and all that kind of represents our identification, but also encodes their priority. And then they go inactive and are recessive, I guess. And now realizes, because it's listening, oh, there's still someone talking on this. Because they're still talking, they must have higher priority than me. So they're going to win. And node B realizes, all right, okay, I got beat. So C just keeps going, right? So this is their ID, and then they start, C starts sending its data payload, and the other frames or packets, bits in this message, right? And then B still needs to transmit, so it waits until the media is clear. It waits for this little period of time, does the arbitration. There's no one else that's conflicting, so when it goes quiet, it doesn't hear anyone else, so then it starts talking. So this is what we mean by when we say that arbitration is non-destructive and bitwise. So C here is winning this arbitration bitwise, and but it doesn't have to, like, doesn't lose any bits in this process, right? It just wins and then starts transmitting the data payload. So here's some just waveforms of what's going on here. This recessive versus dominant frames here, and note that here's your driver input, and then this is your receiver output. This is that differential type signaling, right? Can high and can low there. So, and it's active low, and receiving while we're transmitting there. All right. So CAN messages, it's a broadcast bus. Basically, we're not doing a point-to-point type of thing, or a network switch type of thing. Everything is all messages are present on the bus everywhere. So that may sound messy, but it's very flexible because you can have one wiring harness and you can add in or take out sensors and actuators and nodes and whatnot, just as however you want. And things just work because that data, all those messages are there everywhere, and we don't have to worry about routing them. But not everyone wants all that data, right? So we're going to content filter it by topics. We're going to have 4 different message frames, types or frames: a data frame, remote frame, error frame, and overload frame. And data is the most important one. It's going to broadcast that data, and it contains this identifier that is part of that arbitration process. The more quote unquote ones, I'll say they're the higher priority you have, right? And then we've got just a little frame here that's for timing, and then some control information talking about what else is coming. But here's your important part, this data field. Note that it's 0 to 8 bytes. It's not a ton of data, right? So we're not sending huge long messages. This way, everyone gets a chance to talk, right? Unless you have some super high priority process that's just hogging the bus. Everyone's getting to talk, and there's not inherently a lot of latency, right? If we had really long data fields, then others would be having to wait a long time for all that data to be sent. So there's also some aspects of error rates, and if you have a fixed bit error rate, then the longer packets you have, the higher likelihood that you're going to have a packet error, right? But we have this CRC, cyclic redundancy check. So there's a little algorithm there. If you study networks, you've seen this before, or data transmissions. It's a 15-bit checksum of most of these slots, obviously not itself. and to make sure that not just data, but also his control information, everything is received correctly. And then there's an acknowledgement slot, right? So that's set to 1 in response by any controller that has correctly received the message. So you'll have a bunch of stuff coming back. So there's some delimiters there. So that's, it looks very similar to a lot of other type of data transmission schemes here. Just the interesting thing here is this identification is priority encoded. All right, then we also have a remote frame. This is where you can solicit transmission of data. So if you want data, you can ask for it. A lot of times we're just setting up these things to maybe periodically post data to the bus, or maybe it's an event driven. When something happens, it sends data on the bus, but you can also ask for it, right? And so obviously we don't have a data field here, so that information is going to be in that control frame right there. We also have an error and overload frames. Error is sent when a node detects a fault, right? Not just that we had something that failed the CRC, but really something more as a fault, right? Otherwise, it'd be handled through that acknowledgement process. And the error frame, when a node detects there's a fault, then it sends out this error frame, and that purposely violates these framing rules, right? There's all these rules here. And that will then cause all the nodes to fault. So everyone recognizes, hey, there was a fault on the bus. Maybe that fault gets corrected and fine, but at least then everyone knows everywhere that there is a fault. Then there's overload also, so but it's maybe less important these days. Most controllers have enough memory and speed compared to back in the 80s when this thing was developed, that they rarely overload. But you could conceivably have this and say, hey, slow down. Hardware, so you've got so actually that's the end of CAN right there. So CAN is, I thought I had a kind of a mock-up of a car, but you can imagine that there's lots of different sensors, there's lots of different actuators, there's several, perhaps several controllers, and it is an infrastructure list type of design, but generally there's going to be controllers that are interpreting this data, making decisions, and then posting results of those decisions. That result may go to a dashboard for the driver, or it may go out to some engine control or a logger or something like that. All right, so how are we doing on time? Okay, we're doing good. So I always have to think about time zones here, Central Time Zone versus Eastern Time Zone. Let's spend now a few moments looking at processor hardware. What kind of hardware do you need to run at the edge, right? So if we step back a little bit and think, all right, where we studied all this machine learning, that a lot of that training is going to happen in a cloud or big data center. Tesla has what they call the dojo, that they are constantly training and retraining their machine learning models using data that they collect as Tesla owners drive their cars around, and that data gets sent back and used to update these models, right? And these turns out that problem is really hard. So the overall problem of autonomous driving, okay, so they're supercomputers that are doing this type of work. In Tesla's case, they're dojo, or rank amongst the most powerful supercomputers in the world, right? So supercomputers are used for all sorts of things. One of the things that really drives them is strangely nuclear weapons effects modeling. And that turns out to be an extraordinarily difficult supercomputer task and has driven the development of supercomputers for many decades, especially since we had test bans, so test ban treaties. So now everything's done in simulations. But now autonomous vehicle model training is ranking up there with those type of supercomputers. We're not talking about that now. So that is something that's very interesting, but we don't have time to look at that. This is the hardware that's going to run on the car. Now, you're not necessarily training on the car, but you're still doing your inference, right? So you're not doing a back propagation, but you still need to do the forward propagation in your models, right? And if you're, a vision-based thing, you've got multiple cameras streaming lots of frames per second, and those frames have a certain resolution, RGB values, red, green, blue values, and some number of pixels in that, right? So there's a lot of data moving there. Then we've talked about LiDAR and we've talked about radar, right? Lots of data. So it needs to be super IO rich. Needs to be high performance, right? We've got a lot of things going on. We've got, if we have a lot of cameras, a lot of sensors, then that's a lot of data to digest and process and produce inferences about that. And we've already talked that there's different levels of processing going on, or AI. There's the object detection type of things, right? Perceiving the world around us, tracking things, right? So we have identified a car, but now we're also trying to track it. We're trying to do routing, not just that big route from St. Louis to New York, but how do I stay in my lane around a curve? How do I move to the other lane? When should I do that? When should I get into a right-hand only turn lane? All those type of things, right? And just the autonomous driving itself, right? So we've got, and then there's infotainment, in-cabin functions. Tesla infamously doesn't do a whole lot of monitoring the driver. There's a little bit. You have to kind of rock the steering wheel periodically. But if you look at like what NVIDIA provides and kind of their system that they offer as a starting point for developing your own, they have some driver monitoring with a camera, and it's monitoring the driver. It can tell their eyes, whether their eyes are on the road, whether they're talking on the phone, whether they're sleepy or distracted, that type of thing, right? So, all right, so we'll talk about NVIDIA Drive system and Tesla a little bit. So, NVIDIA's has so some of you all are familiar with the Jetsons that I've talked about, and some of you all are using Jetsons, excuse me. And we all know that, there's GPUs, general purpose GPU systems running on all these data centers. But they also have this hardware and software stack and SDK that's designed for autonomous driving, and they've gone through several iterations of this now. So there's this drive Hyperion. Hyperion, is that how you pronounce it? I'm not sure. Actually, I haven't heard that. Autonomous vehicle reference architecture, and you can follow this link. Maybe I'll do that here, and so you can see their um, thing here, so you can go buy yourself your own AGX Orion developer kit. These are not cheap. So you can follow that link if you want more details on it. And but it's the Drive AGX Orin is a software-defined platform. It is based upon the Orin system on chip, which includes ARM, Hercules CPU cores, GPUs, their deep learning accelerators, DLAs, which I don't know exactly when they came about, but they're fairly new. Then they also have computer vision accelerators dedicated to computer vision. And all of these are packaged up with multiple pipelines, right? So there'll be multiple ones of these, so you can do all sorts of different parallel, not just like parallel processing at a granular level, but you can run different workloads all in parallel and still be accelerating them. And this is all based on CUDA, and your CUDA is their library that you program to actually execute code on the GPU. And I have a graduate course I used to teach on applied parallel programming, and we go into great detail on CUDA. And maybe I'll teach that next year, not in the spring, but someday. Then there's TensorRT, which is NVIDIA's runtime version of tensor type mathematics. And so you can build a big model on the cloud using tons of numerical precision and lots of nodes and that type of thing. And then you can kind of distill it or condense it down to run in a much more efficient manner on lower end hardware, instead of maybe hundreds of GPUs in a server farm. You're just running on one or two of these systems, right? So we need to reduce these things down a little bit. All right, so here's a bigger or kind of a architectural view of things. They have their drive chauffeur and their drive concierge. And so here we've got some safety, automated driving, automated parking, and we can see some of these things. These are hopefully these are making sense to you, maybe a little bit different terminology than we've used before. But yeah, this is kind of the algorithms at the functional level that we're doing. And then we get down into this kind of level of library where you've got your compute graph framework, and how do you actually run through and do your computations, your deep neural network frameworks, point cloud processing if you're using LiDAR, or image processing, that type of thing, ergo motion, ego motion estimation, and whatnot. So then at the lower levels, you might, you're certainly, if you're working with NVIDIA, you're working with CUDA. We mentioned TensorRT. Of course, there's developer tools, IDEs, and debuggers, and that type of thing, and then some other stuff supporting media type operations. And then you might be working with a Linux with some safety extensions, but QNX is a real-time operating system. You may have studied that in embedded systems. Real-time kind of stereotypically means fast, but that's not a requirement of a real-time operating system. A real-time operating system is where you have deadlines that are guaranteed to be met. So deadlines for computation or accomplishing some software-defined action. So in Linux, you don't have that. And in Windows or Mac, you don't have these deadlines. Sometimes when you fire up a program, it happens really fast, and sometimes it takes a while, right? So, all right. So over here on the concierge, we've got this confidence view. If you've driven in some car with some level of autonomy, then you probably see on a display a uh, a moving schematic or interpretation of what the vehicle is perceiving around it, right? So, and if you haven't been in a car, you've probably seen YouTube videos, right, where you might be driving along on the interstate, and there's a truck next to you, there's a truck in front of you, and the confidence view displays that, right? It'll show a schematic of a truck in relative position, or a pedestrian, or construction cones, or something like that, right? So these are not images captured from the camera, they're inferences, right? They're interpretations, perceptions. And that way, as you're driving, you can look at that and you say, oh, my car is recognizing that there's a truck over there. It's not just a bunch of pixels, it's interpreting that as a truck, right? So that gives you confidence that the autonomy package and perception package is doing what it's supposed to be doing, right? So that's an important part of adoption of these technologies. And so then there's these other things, right? So if you look at some of their videos, you can follow that link and you can browse around their whole ecosystem that I provided, and they've got the digital assistant, and where you can ask it to text someone that you're picking up that you're on your way, and it'll route them there, and that type of thing, right? So, or even I think they even in one of their videos say, "Oh, what building is that over there? Oh, it's some theater, and can you get me tickets?" Okay, sure. So, all right, that's not strictly speaking autonomous driving. This confidence view is probably the most intrinsic part of autonomy, and some of these other things are a little bit more peripheral, but yeah. All right. So that was the Orin. Then there's Thor, next generation chip after Orin. Now, I suppose that if you are uh, in the business of doing uh, autonomous driving, and you've got a business relationship with NVIDIA, and you've signed a non-disclosure agreement, then you can get details on their Thor chip. Everything else is what has come out in their press releases and rumors and that type of thing, right? So I've got insider information on some NVIDIA stuff, but not any of this type of thing. It's more to do with their communication systems and whatnot. And so, but even if I did, I wouldn't be able to talk about it, right? Because it would all be non-disclosure. And so that's one of the things you deal with, and kind of these cutting edge type of things, is you don't always get great access to the details from the outside, right? If I went to AMD or Intel and I wanted to get some details on a processor chip I'm going to use, especially like a microcontroller chip or something, I'm going to have all sorts of data sheets and that type of thing. Maybe their latest generation, it might be harder to get ones that aren't in production yet, but in this domain, it's really hard to get specific information. All right, but it adds logic tailored to process transformers. Remember, we talked about transformers a few weeks ago. That's where you had that attention head and these transformers, and it's really key in some of these large language models and a lot of the really exciting stuff that's happened, the generative AI type of things. And so now these have become so important that we're able to create logic that is tuned to actually process those, right? So if you look at like Google has a little bit of hardware. Their tensor processing units, TPUs, and those are processors with cores in them that are designed to process these tensors, right? To be able to multiply all those matrices out, those maybe multi-dimensional matrices and all. So here we're starting to see that transformers are so important that we're dedicating logic to that. It's also interesting that in GPUs you have all sorts of different numeric representations. If you are programming a CPU and you're really getting kind of down in the weeds of like really choosing your right number representation data types, you might be doing that because you're doing embedded programming or something like that, then your floating points are defined by IEEE, and there's a kind of a standard that says this is what a float looks like, this is what a double looks like, whatnot, right? So in GPUs, we've got all sorts of different things. We've got 8-bit ints, we've got these newer 8-bit floating points representations. So basically, this is all a speed versus accuracy trade-offs. There's other sizes, and you can drill down into that on their website, but ultimately it's a speed versus accuracy trade-off. And then we have this multi-domain computing, this ability to partition workloads because we have multiple cores, right? So we have these multiple ARM cores, multiple DLAs, multiple GPUs. So we can partition workloads so that some can run real time on this QNX type OS, while others, such as maybe the infotainment, doesn't need as much rigor, and they can run on Linux or Android. It's significantly harder to develop real-time operating programs on real-time operating systems, and it's not like you can take one processor that's running an RTOS and have a dozen different applications on there. You're gonna end up contending for the resources again, so kind of defeats the purpose, right? So we've got it partitioned so we can do our real-time, hard real-time or soft real-time required stuff on the QNX, and then everything else can go in Linux or Android. And then if one of these guys isn't enough, you can cascade them using this NVLink C2C, chip-to-chip type communications. And that's using some SerDes type of technology, serialization, deserialization, running these signals out over serial lines. So the Thor development kit generally comes with, well, it doesn't come yet. It's still in development, but it will have a pair of chips on it, and then each of those chips have many, many cores on it, right? And those two chips are connected via this NVLink. All right, we can circle back and dive into Chauffeur a little bit more, and it's really geared for this autonomous or assisted driving, has this confidence view, infotainment, driver monitoring, and the concierge service. So I've just kind of drawn this out a little bit. I wouldn't say this is absolutely accurate. There's a number of different ways you can look at these things, but just noting you've got perception modules, right? So this is a package from NVIDIA in their drive system, and you can load up that perception and work on it as a whole kit, right? So then they've got maps and planning algorithms, and then there's this concierge, and this is that user experience and omniverse type things, right? So, all right, then we can look at Tesla a little bit. They've have a hardware 3, they have a hardware 4, and we're just since the summer we're hearing that yes, there's eventually going to be a hardware 5. It's going to be 2030 and beyond or something like that. Who knows? I don't take any delivery dates from Tesla seriously, but Tesla hardware 4 is definitely a thing. And again, it's this kind of definition of compute plus a sensor package. So, and it gets adapted per model car, but it's that idea, just like with NVIDIA, that they're talking about a whole ecosystem, right? There's the cores inside the chips, inside the boards that are really connected to a bunch of cameras over a bus and radars and lidars and displays, all that type of thing, running multiple different applications and workloads, right? So the hardware 4 is, you should think of it in that term also. There is like, CPU from Samsung, 20 CPU cores at 2.35 gigahertz, 3 of their neural network processors running at 2.2 gigahertz. Now, what Tesla does is similar to what they're doing with their dojo is that, most of us run our machine learning training and inferences on GPUs, and turns out that the GPU is originally developed to render pixels on a screen, images on pixels on a screen, but it turns out that that's super in what we call embarrassingly parallel type operations, and there's a lot of general purpose type applications that are likewise parallel, and so can be deployed on these GPUs, right? So, but there are certain things that are needed in autonomous driving that maybe are more specialized than if you're doing actuarial tables or something, trying to evaluate life insurance policies or something, right? So there's some customization going on here, but it's, if you're in the numbers, 50 tops, 5 megapixel cameras, and even though this every article you read on it talks about the ARB Phoenix radar, because there's connectors for it, there's hardware for it on this hardware 4 board, and so that's, even though Elon Musk has said, we don't need radar. We're doing everything with vision. They've removed radar, removed even ultrasonic sensors, and they've never had lidar on their systems. So, but there is this radar here. So when we looked at the FMCW radar, we used TI as kind of our base case. You had in your home assignment, you had a data sheet from TI, but Phoenix is another major. They're doing all the tricks we talked about. As when you go to MIMO type processing, where you have multiple transmitter antennas and multiple receive antennas, you can get closer to an imaging type of radar. So so here's, we looked at this. This is NVIDIA's drive, Hyperion, whatever, their chip, and that's the Thor. So if we start digging into these guys, you'll see that let's see, where can I No, I don't want that. I should have kept all my tabs open before because I had some interesting things. Okay, so here you're seeing that the in-cabin driver monitoring and even passenger monitoring is they're claiming that they can isolate their eyes and see which direction they're looking. They seem to indicate that they do a little bit of facial recognition so they can determine one driver versus another and that type of thing. And I'm sorry, there were some links that I thought were interesting. Maybe I was just doing that, or was it? So here they have their talking about their perception module and their mapping module. So that looks similar to what we studied out of the book. And then the planning module, and then this is their whole little um, concierge digital assistant type of thing. So I think that this one is, and then we'll take a break. And then we'll talk about Ross. So this is the example I was talking about. So if you want to go take the break, we'll be back at 8 o'clock. So you see, this is that confidence view you see on that center display, where you can see how it's perceived, the road markings, and the path that it's taking, it's projecting. Cats, come on, there's so much better shows than Cats. Okay. We will meet back again in about 10 minutes.